Good morning, students. In today's class, we'll see about the stacks and queues. Stacks and queues are the data structures. It is the way in which the data can be stored in a system. When the program is under execution, the way in which the data required for the program can be stored is the data structure. So this stacks and queues are one type of data structure, a type of method in which the data can be stored. Now, when you are arranging something, like when you are arranging the plates one above the other, so there is a fashion in which the plates can be arranged. Okay, when you are putting the disk on the disk cylinder, so the disk are put one above the other on the cylinder. So you're putting the disk one above the other. So there is an order in which the disk can be stored, or the plates can be stored, or a car can be parked in the parking lot, vehicles can be parked in a parking lot. There is some fashion, some method in which, some way in which the vehicles can be parked, correct? So similarly, there is a way in which the data can be stored in the memory. Okay, so two of them, two of the method is the stacks and queues. Other than this, there are many other methods. There is B tree, B plus tree, many other, and the circular queues. Okay, so there are many other methods. I'm just introducing to these two topics, the stacks and queues. That is the data structure, the way in which the data can be stored in the while the data is used in the program. Okay, so coming to stack, we'll just see what is stack. Stack is a data structure, is a method of storing the data in memory, so such that the elements can be stored one above the other. The data can be stored one above the other. Okay, so the data is stored here, 43, next data is stored here, one above the other. The data are stored. Okay, so, and there is one entry point and one exit point only. Okay, so this type of structure is called the stack structure. We'll just see the stack. So this is the stack in memory, stack of words in memory, that is reserved bytes. Okay, so this many bytes, this many memory locations are reserved for the stack. And then, so in stack here, now from this location to this particular location, the memory is reserved. Okay, and the data are added to those memory locations. Now, this indicates the bottom of the stack, this particular location, and this is the bottom element. Okay, so 43 is the bottom element. Next element, suppose I want to store 13. 13 is stored on top of this. Next element on top of it. Okay, now suppose I want to retrieve an element. Now, at this condition, I can retrieve only 50. Okay, that is whatever is the topmost element in the stack, that element can be retrieved. Okay, that is when there is a number of plates, stack of plates, we see one above the other. You take the topmost plate, correct? You don't pull a plate from in between. It is not possible. You take the topmost plate. Even if you don't like the plate, you keep it down and take the next plate. Correct? So similarly, you have to take the top element only. It is in this particular structure. You can take only the topmost element. Okay, so only one entry. So one entry. From that entry, data is added to the top, and data can be taken from the top itself. Okay, so whatever element you enter last, that will be the first element to be taken out. Okay, so whatever element is entered last, that will be taken out first. So it is a structure called as LIFO, last in, first out. Okay, whatever element is last is put in last, that will be the first element to be taken out. Fine. So this structure is called the data structure, this stack structure. So this type of storing of data, right? Now, so now at this particular condition, this is the topmost element, okay? There is a register, stack pointer register. So in stack point, the stack point register contains the address. It is a pointer to this location. It contains the address of this particular topmost location, okay? Now I want to add the next element, suppose. So address is incremented to the next position and the data is added. Fine. So that is the stack structure. That is the stack structure. Yes. So that is the current element. Fine. So stack is a data structure in which elements are stored one above the other. There is only one entry point. Okay, data is added from this position and data is also removed from this top position. It cannot be pulled out from in between. Fine. So this type of structure is called as LIFO. The element which is put last in will be the element to be taken out first. Okay. So last in, first out structure. That is stack structure. So as we add the element, the top pointer or the top position, that is a stack pointer, will point to that particular location, topmost location. As you add, suppose 40, I add, stack pointer will be pointing to this location. Okay. Now I add 60, suppose, stack pointer will be pointing to this location. Okay, and this is the topmost element. Fine. So this is the stack. So this is the stack memory location. Name elements are added to the stack one by one. And this is the top position of the stack pointed by stack pointer. Okay, stack pointer is pointing to this location. And you can see the addresses. These are the memory addresses. So it can be any address. At any address, the data can be stored in any address. Suppose this is 1000, this is 996, and so on. 992, and so on. Okay. So as I told earlier, I'm considering this as a 32-bit machine. When it is a 32-bit machine, it is in the multiples of 4. Okay. So it is in the multiples of 4, and hence the address differs by 4 bytes, 4 numbers. Okay. So this is the LIFO structure, last in, first out. The stack has two properties. Okay. Two features of the stack. As the elements are added to the stack becomes full. As the elements are added to the stack becomes full. And when the stack is full, no more elements can be added to the stack. Correct? That means if suppose I added the elements, topmost element is 46. I have added all the elements here. Fine, elements are added, the datas are added in this location. Now the stack is full. I want to add 30, suppose. I cannot add as there is no space which is free. That means the stack is full. Okay. One more condition is, suppose I have removed all the elements. I have read all the elements and all the elements are read. In that case, there is no elements in the stack and the stack is said to be empty. Okay. So there are two operations which happens in the stack, that is adding the elements to the stack, that is called as push, and deleting the elements from the stack, it is called as pop. Okay. So adding the elements to the stack is called as push, and deleting the elements from the stack is called as pop. So when push happens, when adding of data happens, there can be the condition of full, the stack becomes full. And when deletion of data happens, I'm removing the data from the stack one by one. When removing of data happens, there can be the case of empty. The stack becomes empty. Okay. Now the two main, there are many different applications of the stack. So one of the example of the stack is it helps in the nested function call. So we'll see what is function call and what are subroutines in the next topic. Okay, so or you can say like I have an expression for being solved A star B. Okay, in postfix expression I can write it as A B star. Now when I want to solve this expression, as the elements come, as the operands come, I put it to the stack. I put A, and next B is read. I put B. Whenever the operator occurs, whether it is any arithmetic operator, plus, minus, multiply, or divide, whenever an operator occurs, I take out the previous two elements from the stack, the topmost elements from the stack, and this particular operation is done. Okay, so as it is only one entry, the topmost elements will be the operands of this particular operator. So one of the application is to solve the expression. The other is in nested, in case of nested functions, to call to store the return type. We'll see that in when we are seeing the topic of subroutines. Okay, and parameter passing, the parenthesized any type of equation solving. So in all such cases, the stacks are used. Okay. Now there is push operation and pop operation. Push is adding of elements to the stack, and pop is deleting of elements from the stack. Okay. So we'll see how the push function works. Pushing an element to the stack, or pushing the data to the stack. So as you had seen earlier, okay, as you had seen in this case, whenever the elements are added one by one, okay, so the elements are added one by one, I add the elements one by one, correct? Now here, when I'm pushing the elements, suppose this is the address of this particular location as I take it as 32. Okay, so this is 28, or 1 second. I'll take this location as 1000. Okay, I'll take this as 996, 994, and so on. These are different memory locations, memory addresses. Okay, different memory addresses. I assume that this memory is of 32-bit. Okay, so 32-bit means it is of 4 bytes. Okay, so for all the addresses, there will be it will be in the multiples of 4. So 1 second. Okay, so it is in the multiples of 4. Okay, so I think I have made a mistake. It is 992 here. Difference of 4 I told, and it is 988, correct? So 998, these are different memory addresses. Okay, I told it is of 4 bytes. So the address differs by 4 values. Okay, if this is 1000, this address location is 996, the above is 992, and then is 988. Okay, so I add the elements in those locations. So whenever I'm adding, you can see that the value is the address is decremented by 4, as it is a 4-byte machine. The address is decremented by 4, and then the element is added. Okay, decrement by 4, the stack pointer, which points to the topmost element of the stack, is decremented. So this pointer is made to point to the next location, and element is added there. Okay, so we'll see the function, the instructions for this particular push operation of stack. So the push operation of stack, I'm assuming a 32-bit machine. So in a 32-bit machine, as I told, it is 32-bit machine. The addresses differ by a value of 4. Okay, so wherever the stack pointer is pointing to, suppose here I have entered 43, and next I want to enter 53, the data, then the stack pointer value, whatever is there in the stack pointer register, what is the value stored now? It is 1000. It has to get decremented. Okay, it has to get decremented by 4. 1000 minus 4, I get 996. 996 will be stored, and from to this I'm pushing the data. So stack pointer is in this location, so to this location 53 is added. Okay, so the push operation goes like this: subtract 4 from SP value, from whatever is there in SP, subtract 4 and put this value in SP. So SP content now is 996. Okay, means SP is pointing to 996. And now move the new element to this position. It is what type of addressing mode? It is what type of addressing mode is present there? Okay, it is indirect addressing mode. Okay, so SP contains the address where the data is, address of the operand. Okay, so at this address the data has to be added. 53 will be added. Fine. This is the push operation. Push operation can also be written as auto decrement. This particular instruction, move new element to minus SP. Okay, minus SP, wherever SP was pointing to, it is auto decremented minus. Fine. Similarly, for pop operation, what happens in the pop operation? I have to remove an element. I have to take out an element. So that means if it is 1000, okay, and here some other data is there, 53, and here it is 43. Stack pointer is pointing to this location at 996. Okay. Stack pointer is pointing to this location. Fine. It is at 996. Pop operation, I take out the element and move the stack pointer to the next element, topmost position. I have removed this element. Okay, I take out, move out this element, pop the element out. Okay, and next stack pointer should be pointing to the value plus 4, this particular location, next location. Okay, so the pop is move the value that is pointed by SP at the memory location stored in SP. The value whatever is there is moved out to a variable by name item. Item is a variable. Okay, in this variable item, the value 53 is stored and SP value is incremented. So it becomes 1000. So SP is pointing to this location. As this element is not there, this is the topmost element of the stack now. Okay, so another the instruction can also be written as, it is as an auto increment instruction. It can also be written as move the content of SP to item and then increment. It is post increment. You have seen the auto increment instruction. Okay, so these are the instructions for pushing an element to the stack and popping the element from the stack. Now, as I told earlier, when you are adding the element to the stack one by one, you are adding to the element to the stack, you must also check whether the stack is full. If the stack is full, elements cannot be added. The programmer will must check whether the stack is full before adding an element. Okay, so the conditions to be checked in the case of push is check whether the stack is full. Okay, if the stack is full, no more data can be added. If it is not checked, the data is stored in some other location which is not accessible. Fine, you store in a different out of range area of the memory. Similarly, the pop operation, when you're taking out the element from the stack, it must be checked whether there is some element in the stack. If there is no element in the stack, then it retrieves some other values and operates on other values. Okay, so stack is still here. It is trying to retrieve some other values which is there, junk values. So pop operation must check whether the stack is empty. Okay, if it is so that before accessing the data and taking the data, it must check whether the stack is empty. Otherwise, you will be retrieving a junk data. Okay, out of range again, the other memory locations area which is not in stack. Okay, for this, yeah. So you must check whether the stack is full. So for this, to check the stack is full, I have taken this example of the stack. So this is the content of the stack from memory location 1500 to 2000 is the stack content. Okay, the stack data is added in these locations, going on till 1500. Okay, now first we'll see for the push operation. Now for the push operation, I should check whether the stack pointer is present. Okay, I should check whether the stack pointer is present in this particular location. Okay, so fine. So if it is other than this range, if it is somewhere outside, SP is pointing to this location, then it is out of range and data cannot be added to the stack. Okay, so that means the stack is full. So how do I check the stack pointer? Where is stack pointer? And I should know the value. I know in stack pointer there is the address. Suppose this is 1496. Okay, so 4 numbers difference in this stack pointer. Fine, I'll have 1496 if suppose the stack is full. Okay, I can use a function called as compare. Okay, an instruction by name compare. So I compare these values, 1500, the topmost element of the array, the topmost address of this particular stack, and the stack pointer value. Okay, so compare this topmost address of the stack with SP. So what happens? It compares the values, that is the subtraction, SP minus 1500 happens. Okay, so the compare instruction, what it is doing is compare source comma destination. Okay, two operand, source and destination. How does it compare as DST, that is destination, minus source. If it returns 0, that means both are the same. Okay, both are the same. That is, if this is 1500 and this is also 1500, then it returns 0, the subtraction. Okay, so compare means subtraction of those values happen. Okay, the difference is found. Now, if suppose ESP is pointing to this location, 1996, means the stack is full. Okay, I have incremented and I want to add the element to the particular stack, but it is incremented to this location. The stack point is incremented to this location of the memory. Okay, so ESP is 1496. When I compare, I get a negative value, minus 1500. That is destination minus source. Okay, 1496 minus 1500. I get a negative value, less than 0 value. So if it is a less than 0 value, okay, it is a less than 0 value, means the stack is full. There is no space in the stack. It is an error. Okay, it is an error if this condition does not occur. If this condition is false, okay, that means the stack is not full. In such case, the element is moved to the stack. Okay, in such case, the element is moved to the stack pointer. Fine. Now, that is the condition for push operation. I compare the ESP pointer and the topmost position of the stack. Next is pop condition. So pop condition is to remove the elements from the stack. If the pop point, the stack pointer is in, okay, if the stack pointer is in this particular location, okay, so there is one element to be popped out, and if it is in a different location, there is no more elements to be popped out. Okay, so pop operation, I compare this values. Okay, so ESP, suppose it is pointing here, so 2004, that is ESP value is 2004 minus 2000, the value is 4. Okay, so if it is a greater than 0 value, it is not 0, it is greater than 0 value, means the stack is empty. Okay, in such case, if the stack is empty, then it is an error message. The error message is displayed. Otherwise, the data is added to the stack. The data is moved out from the stack pointer to the variable, item variable. Okay, now two operations, that is the push and pop operations you have seen. Okay, you have seen the push and pop operations. So this is the push operation. You are adding the element. Okay, so when you're adding the element to the stack, move the stack pointer to a particular position and then add the element there. I'm adding the element 53. Suppose I want to remove the element, okay, from the stack, take the element from the stack, okay, and the stack pointer is moved to the previous topmost element. So now this is for the task to be done for adding and removing the element. Okay, so before this addition and pushing and popping of elements, the condition should be checked whether the stack is full or empty. Okay, if the stack is full, the push operation cannot happen, the data cannot be put to the stack, and if the stack is empty, the data cannot be taken out. There is no data. Data cannot be taken out of the stack. Okay, so that is the stack operations, the push operation and the pop operation of the stack. Fine. And so next we'll see what is queues. Okay, queue I told is a data structure. So it is an arrangement of data in a different pattern, not the stacked way, in a different pattern. So it is similar to a queue, which is followed when you are standing for a ticket in a queue. Okay, or the queue system, what is followed. Okay, that is, there are two entries. There are two entries. We'll see, like the element is added at one end and exited from the other end. So push the element, put the element to the queue and take out the element from the queue. Okay, so two ends. It is not like stack, not only one end, there are two ends for queues. Fine. So it is, there are two ends. It is called as the rear and the tail. Okay. Rear is the end. Okay. The rear end and the front end. Okay. So the rear end is where the data is added, and the front end is where from where the data is removed. Fine. So here you can see the element is added to the queue. Okay, so this is the rear end, and the element is removed from the queue. So this is the front end. Fine. So it follows the system of first in, first out. As you see in the ticket counter, you stand in a queue for the tickets. You stand in a queue for the ticket. The first person who has come will be the first person to go out of the queue. Whoever comes first in, he will be the person to go out first. Correct? So this follows the first in, first out system. Stack follows last in, first out. Okay. So there is front end. There is the end which is to which the elements are added is called the rear end or the tail of the queue, and the other end is called the from where the data is removed is called the front or head of the queue. Okay, so front or head of the queue, and this is the rear end or the tail of the queue to which the elements are added. Fine. So this is the introduction about the queues. There is no, you need not see any code or anything. Okay, so just an introduction of what is queue data structure is given. Fine. Again, in this, there is the circular queue, double-ended queue. Okay, so many other queues which you'll be learning in more detail in the data structure subject. Fine. So this is okay. Right.